Okay, it's 4 o'clock, so we probably need to get going. Hopefully some of the folks, as the beer dries up, maybe they'll wander in here. But let's go ahead and get started. I'm really, really excited to be a co-chair for this session. I'm Lori Glaze. I'm the Director for Planetary Science at NASA.
And Toshi Hirabayashi from Auburn University.
Yeah, so we're very excited to be chairing this session focused on small bodies, spacecraft, asteroids and comets journey to the origin of the Earth. And of course, this is, for us, a very interesting topic because, of course, we find small bodies in multiple different populations across the solar system. And by looking at examples that are found in each of those different populations can tell us different parts of the story about how the solar system was formed and how it has evolved. And so when putting this session together, what we tried to do was not just focus on single missions and what that one mission is doing, but actually think about how the whole is greater than the sum of the parts. And so the fact that we have at this point in time so many wonderful missions that are visiting different types of small bodies across the solar system, trying to think about that from the larger perspective, how putting them all together, what we can learn. So we've asked each of the speakers to not only talk about their own mission, but to try and think about how it fits into the greater context. In the speaking today, we've got rapid, almost lightning talks, almost. We've got 10 minutes for each speaker. The light will turn yellow at 8 minutes. And then we have another couple minutes to sum up when it turns yellow, and then we've got 2 minutes for questions, and then at 12 minutes it will turn red, and we need to change speakers and keep moving in order to stay on schedule. What was the other thing? Oh, I've been told we need to let you know that it is okay to take pictures of the slides for your own personal use. If a speaker does not want you to take pictures, they should either have the little AGU logo that says no picture taking, or they should let you know in advance that you can't take pictures. And then I'm going to pass it over to Toshi to tell us about what we're offering following the session.
Okay, so after this session, we are going to have a happy hour. The location, first of all, anybody who are interested, please come. And then the location is Marriott. The atrium on the second floor, just right across the registration desk and the bar. So we will have a happy hour. The time is 6:15 p.m. Right after the session. So please feel free to go there and have a happy hour. So.
That's your reward for coming to the last session of AGU. Okay, if you can put the slides up, I'll introduce. We'll go ahead and get started. The first talk this afternoon will be, it's on this one. Here.
Oh, sorry.
Yeah,
that's right.
The first talk this afternoon is going to be on the evolution of asteroid Ryugu, revealed by Hayabusa 2, and implications for sample analyses, by Seiji Sugita.
Yes, that's
okay.
Right.
And he'll be talking to us about Hayabusa 2. And we're going to figure out the AV by about the last talk, so just be patient.
Yeah, thank you.
And then the start.
Hit start.
Yep. Let me see if I can fit in 10 minutes. All right. I'm Seiji Sugita of University of Tokyo. I'm a Hayabusa 2 ONC science PI. And today I'd like to talk to you about what we learned out of Hayabusa 2 and about Ryugu. Okay, we have two major science goals for Hayabusa 2. One is to, is this the other cursor? Okay, yeah. The chemical or materialistic evolution of the early solar system, including parent body process that really sets the ingredients of life on the planet itself, so that's very, very important. Second thing is the dynamical and collisional evolution of small bodies, and then resulting bodies would be rubble pile. It's a self-gravitating bodies, and then that can be used really well with as an analog for planetesimals. So that was the premise behind the mission. And then we had a series of instruments starting from visible cameras, infrared spectrometer, thermal infrared imager, the LiDAR, and then 4 landing rovers, small carry-on impactor, and then sampler. Okay. Oh. Okay. Oh. Yeah, this is a busy diagram, but it just shows you how busy we were since the arrival in the end of June. We started with such a low-resolution image of Ryugu, but quickly the resolution got really well, all the way to a 6 millimeter per pixel after the first release of a rover. And then the successful touchdown happened, and then we observed the things at the 1 millimeter per pixel resolution and then dynamical response to the surface. And then moving on to the crater formation using a small carrion impactor, we made this a semicircular crater on the surface of Ryugu. That was a really successful experiment. Then later on, we touched down somewhere around here on the ejector blanket from this artificially made crater in 11th of July of 2019. And then follow-up observation was conducted, and then didn't have much time to really have a little hiatus. And then we had just a final farewell to the asteroid Ryugu, and then heading back to the Earth. And then hopefully next year about this time, we'll have sample to the Earth. Okay, before I move on to the science discussion, I'd like to point out two things. One is that our best product may be this kind of a beautiful map. This really has a important information. Look at this equatorial ridge and the subtle variation, albedo and so forth. The real point here is that the good calibration, really sober, no flashy, but the very important data reduction are the key for the good science. And then to do that, the NASA participating scientists have been made a really wonderful, indispensable contribution to our team. And then similarly, the OSIRIS-REx collaboration was also irreplicable. It was really useful. And then on the top, the pre-touchdown observation on the surface by the MASCOT supplied by DRL and CNES was extremely useful. And then that really made us feel, oh, good, we can go. And then those international collaboration with the broad science community was really benefiting to the HyPSA 2. All right, so now what did we learn? That's the whole idea about this the talk. A lot of things, but the first look was that the Ryugu was extremely circular, top-shaped asteroid. That was the first impression. The impression was correct. And then the second thing is it's a rubble pile. The density is very low, and then porosity is as higher than 50%. And then also a large amount of large boulders everywhere on the surface. That's probably coming from the parent body of a Ryugu. So it's probably disruption fragments of a parent body. And another aspect is that its spectral and albedo characteristics are consistent with the Polana and Eularia families that sits in the inner asteroid belt. That actually has a very important implication for the evolution of possibly life on Earth, because this particular families are the one that delivers the greatest number of C-type asteroids through the new 6 to the near Earth. So depending on the nature of these guys, the ingredients of the material, not in the beginning of the origin of life, but the later evolution may be fully, extremely influenced by those guys. So that's what we are about to learn. Okay, so, and then the third thing is that the spectral characteristics of Ryugu here is not consistent with the our conceptual CMCI usual carbonaceous chondrites, much darker than those. But rather, this is more consistent with the thermally metamorphosed or possibly shock dehydrated carbonaceous chondrites. And then IDP cannot be ruled out. That's another possibility. But those are not really what we are anticipating before the arrival. So that was really interesting and then surprising discovery we had. However, I think what was most surprising to us is not from my camera, it's from our neighbor's near-infrared spectrometer. The OH absorption band at the 2.7 was relatively weak. It's much weaker than those typical CMCI chondrites, but close to this type of thermally treated meteoritic samples. And then even more surprising thing is that in the Bennu by the OSIRIS-REx had a very classic hockey shape check mark type of absorption at the 2.7. But the rest of the characteristics are very similar. You can't really see the difference between this asteroid and that. I mean, except for that one is published in Nature and the other one is from Science, but it's a very two different asteroid. Very similar density and then darkness and then the visible spectra. Yet the absorption of OH is contrastingly different. So what does it mean? Are they coming from the same parent body in the different parts or different parent bodies? That's it's a very hard question. It's a very interesting question. It's going to really bother us and excite us for probably at least years in time, possibly if not decades. And so that's one good benefit of having two similar asteroid mission going on at the same time. Okay. Further deep into the investigation revealed that we have different morphological types on boulders on Ryugu, and then that was confirmed by the MASCOT observation on the surface. And I'm not going to go into the details of different types, but the point here is that those different types of morphologies of boulders may be coming from different parts of a parent body. However, if you plot the spectra in this PC space, those individual points are the boulder characteristics, but those are within a small range compared to the entire main belt distribution or the laboratory experiment change of a color of a spectra of a CMC chondrites. The range is much more confined. I would say it's very uniform. And if those are coming from really different parts of our parent bodies, that observation suggests that parent body of a Ryugu would be rather uniform, not this type of a classic onion shell. Possibly some thermal skin depth on the near the surface. So uniformity is something we learned. If this is really correct inference, then it would suggest, it would support the aluminum-26 type of uniform heating on the parent body. However, extremely primitive type of interior cannot be either ruled out. So that's another thing we have to keep in mind. However, this is another important piece of information. So this is the beginning of the evolution. And then later on, when we further look into the details of the surface boulders, we found so-called bright boulders or bright spots, and much rarer than these four types of boulders on the surface. But some of them are actually S-type or Q-type spectra. You can see the drop up here and then 1 micron absorption. Those are classic silicate absorption. And then those are actually pretty large, and then it has to land on a soft low speed. To do that, I'll make it short. Those are too large to accrete on the Ryugu after it has its own current mass. Otherwise, a catastrophic disruption would occur. So our inference is that those S-type or Q-type bright spots or bright boulders are probably fragments of an impactor to the Ryugu's parent body in the past. Furthermore, this is a breccia-looking boulders on the surface, and on the top, actually, it's probably mechanically attached to this the boulders. The breccia. This is probably mechanically attached. So this was probably incorporated in this boulder before the formation of the breccia. So it must be really old. So that really also supports the old formation time of this thing. Okay, further down in the timeline, we have evidence for the past fast spin. The current geopotential is consistent with the high geopotential equatorial on the polar region, and then stable in the mid-latitude. But when you increase the spin rate about twice as much, Watanabe et al. Found out that the relative slope is close to the angle of the reports all across the surface. That would support this pole to the equatorial slides of the material. And however, when you look at the surface, oh, this is yellow. I gotta read it, yeah. I gotta go, yeah. The surface flow is opposite. That's consistent with the current spin rate. So recent spin down was probably happened. All right, making things slow. And then the red-blue crater, I'm not gonna talk about details, but those blue craters formed after the end of a solar excursion of the Ryugu, that was baking the surface red. And then the age can be measured because the SCI crater really gave us a good scaling law. All right, this wrapping up, we have 5 at least different stages of evidence of anchor points of very complex evolution Ryugu from a parent body all the way to the current stage. And then we would think that HIVES-2 samples may contain those key materials from those different evolution stages of Ryugu, and then it will be useful for comparing with the Bennu, and then maybe tell us about the evolution history, migration in the past of the Ryugu. So stay tuned for the sample return next year. Thank you.
Thank you. I know these are going to be really fast, but I'm afraid we're out of time for a question. So we're going to, when it turns red, we're going to have to switch. So I told you these are quick talks. They're speed talks. But please be sure to corner people and ask them questions after the session if we run out of time. The next talk is going to be OSIRIS-REx at asteroid 101955 Bennu, selecting the prime and backup sample sites, and this is going to be given by Heather Enos. And of course, we just made the selection announcement yesterday of the primary and backup, so thank you.
Okay. Good afternoon. Oh,
Sorry.
and
Reset.
advancing is
That one.
Oh.
So we use key
here.
Oh, yes.
All right. All right, so I am going to make this as quick as possible. So OSIRIS-REx obviously is an asteroid sample return mission, and our mission objectives are very relevant to our small body exploration and feeding into the overall goals of the agency to learn more about small bodies. We are interested in understanding the origins of the solar system and how that impacted the Earth as we know it today. You know, how did we get life here? So Bennu is really a time capsule that we will be opening and checking to see where did we come from and possibly where are we going. Resource identification is an important thing that we are studying, and this will give us insights in terms of are there resources available for us to extract that will allow us to use them for future exploration to other planetary bodies that we haven't yet explored. And then security. Security is really important in terms of how do we protect the Earth. And so Bennu is considered a potentially hazardous asteroid with a 1 in 2,700 probability of impacting the Earth in the 26th century. And we're going to get up close and personal with this asteroid and study its orbit and its trajectory and further characterize how it may evolve over time, and will it increase in probability or decrease in probability of impacting the Earth. Okay, so let's talk about the site selection and what we've been doing since we arrived at Bennu last December, just a year. So what I want to emphasize here is during development, we had a very rigorous way of creating all of our requirements across the system, including site selection, what we thought we would need in order to make the decision that we made this week. And those 4 criteria and requirements included safety, deliverability, sampleability, and science value. What I want you to know, and thinking back in time, is safety and deliverability and sampleability all had very specific probabilities that we were a little bit naive in thinking that we were going to independently get those values for each of those inputs. We were going to weight them, we were going to put them together, and we were going to get the value that was the best where they all intersected, and that was going to be the site that popped to the top. Well, it wasn't quite that easy, and we had to get a little innovative in terms of how we got to our conclusion. Okay, so getting the data takes a village. It takes a lot of inputs, all the way from designing the original baseline mission and making sure that you bring along what I call a toolkit, which is our payload and our spacecraft capabilities that are going to allow us to achieve the observations necessary to get the data. So that's the very beginning, but I like to call our process what I call stractical, And the reason I call that is you start with the strategy, but as you learn as you go, you're on a tactical, then you're tactically changing what you need to do in order to accomplish your goals. And so that requires a really tightly integrated team and process from the engineering team, through the science team, through our ops implementation team. So I can't emphasize enough how that close communication has allowed OSIRIS-REx to be able to react to the things that I'm going to talk about that made us have to change some of our processes and our quantification and qualification of our sites. Okay, so I hope many of you have seen this already, but through this process, through Approach, we did a lot of global mapping. We collected global information that allowed us to get what we were about 50 regions of interest in the spring of this year. And that was our first opportunity to start our process of ranking and coming up with how we were going to calculate our deliverability probability, safety probability, and sampleability probability, at which point we realized it wasn't going to quite be that easy, mostly because we had a very, very rugged surface that we didn't anticipate. We also found that the thermal inertia data that we had from ground-based observations that led us to believe we had a lot of fine-grained material wasn't exactly correct. And so these things started to make us understand we really needed to take a step back and figure out how we were going to first winnow down our ability to meet our deliverability and safety requirements. And so that was our first step. And going through a lot of that data and that process, we were then able to get to our final four by the summer of 2019, realizing at that point that we would start to focus on the sampleability aspect and where on Bennu did we really have an opportunity to find fine-grained materials with the highest science value. And put those sites forward into going into what we called a reconnaissance A phase, of which we spent a week campaign on each site, doing very detailed high-resolution imaging of each of the sites and getting the spectral data that we needed to start to understand how we were going to continue to rank these sites and make a selection. Okay, so I've talked a little bit about the unexpected and where the challenges, the main challenges in site selection started to creep in. And so what we encountered was, what we built the system to be able to do was to navigate to a precision of about 25 meters in radius and expecting to be able to find many areas that had that sites that were 25 meters in radius that were smooth and hazard-free. We haven't found anything like that to date. And so what we started to find were sites that were maybe going to get 5 to 8 meters in radius of hazard-free and safe sites to go to. So one of the things we did during development was we actually put in the hooks for something called natural feature tracking, image-based navigation to the surface. And we debated a lot during development whether or not we should, in fact, put this hook in, because it was an expensive insurance policy to take with us. But thank God we did. That's a good lesson learned. And we didn't put it in with the idea that we needed image-based navigation to go to the surface. We actually put it in as a backup to our LiDAR system, just in the event our LiDARs failed. We needed to have another option to get to the surface. So in hindsight, we built in an insurance as a redundancy to a possible failure of hardware that gave us the opportunity to enhance our capabilities to get to the surface and navigate to a much smaller precision than we anticipated. So once in a while, you get lucky. Okay, so at this point, we refined our capabilities, we added capabilities. We really looked back at the system to see what margin we could take out of the system from a spacecraft safety perspective. You know, how could we relax some of our back-away hazard requirements for tip-over? We went through a lot of effort, both on the engineering side and the science side, to talk about what could we relax in order to open our options for sites. And now at this point, we were really focusing on sampleability. And we are a sample return mission, and our level 1 requirement is to return at least 60 grams of pristine carbonaceous sample. And that became our focus. again, it's our driving requirement. This was another area that required us to go back to the drawing board and figure out how, in fact, do we quantify the material that is accessible and that we can ingest into the tag SAM head. And this took a lot of work, and I was talking to Hal about this earlier. Kevin Walsh, our Regolith Development Working Group lead, genius guy, he really had to reverse the process of looking for smooth areas. We thought before we wouldn't have enough areas to use natural feature tracking. It was quite the opposite. We had to really hunt for areas that were unresolved in images up to this point to make a determination of which ones had a higher probability of allowing us to meet our level 1 requirement. Okay, so that got us to our final 4 sites. I'm going to speed this up and let you know. Nightingale is our site, our primary site, and Osprey is our backup site. In the event that we are not successful the first time, we will move to our backup site and go to Osprey. Okay, just an example of our sampleability maps. And this is the Nightingale site with an example of what we call a hazard map that we've also employed to ensure that we maintain safety of the spacecraft as we descend to the surface, that allows us to detect hazards and do a wave off or a back away autonomously in the event that we detect a hazard that's not safe for us to go to. So that's it.
Thank you.
All right. We do have time for a question.
Will the LiDAR be used for landing at all?
Will the LiDAR be used for landing at all? I just want to make sure everybody can hear.
The answer is the LiDAR will not be used for landing. It just doesn't have the precision that we need to get. It would not allow us to get to the precision of 5 meters, of which we're required to get into these surfaces, or these spots. Yeah. Yes?
How about the disconnect between the Earth-based thermal inertia measurements and what you actually see there?
Yeah. How about that? Yeah. Josh Emery's working really hard to explain himself. Yeah. That's what I tell him every day. That's really a head scratcher, Nancy. It's something that we really, what's interesting is the largest boulder on Bennu has the lowest thermal inertia, so it doesn't completely make sense. I mean, it's a good scientific mystery that needs to be worked on. Yes, Hal?
I
I
think
just want to clarify that question, right? Because it's not that the ground-based observations were wrong, right? It's just the interpretation that low thermal inertia implies.
That's right.
You are correct, yes,
Okay.
that is true.
Josh says the boulders are great. Is what he told me.
I call them very friable, and we'll crush them if we have to. We're going to crush them if we have to.
we're going to need to, well, you've got 30
One
seconds.
more?
Go ahead.
Okay, go ahead.
Are you going to be able to get any estimates of variations of porosity within the body from gravity data?
We have I don't think we'll be able to get that level of precision. I don't think so.
Okay. All right. Thank you, Heather.
Thank you.
All right. Thank you for that one. The next talk, while we try and pull these up, is a
PC. I'm trying to.
in situ investigation of asteroid 162173 Ryugu by the Hayabusa 2 MASCOT lander. The talk will be given by Matthias Groth.
Yeah.
Okay.
And then when you choose the change the slide you want to use.
Okay, we need to hit the button here. That button.
Next one.
Okay,
The swap to this PC.
Oh yeah, that's right.
we're ready to go.
Yes.
So this one's going to be about the MASCOT lander, so the Mobile Asteroid Surface Scout, which is part of the Hayabusa 2 mission. Seiji saved me some time to introduce Ryugu on a global scale, so I'm more focusing now on what we can see with a landed asset. And here's the asteroid as you know it and love it. So basically, C-type asteroid, one of the building blocks of the terrestrial planet, so that is what these things look like. And of course, what we are interested in is how do these things form, how do they evolve, what are the ingredients, and some of these things you can answer, of course, already as we've seen from orbit, and Hikaru is going to talk later about what you can learn from the samples. But what I'm going to talk about is what you can learn extra on top of that if you have a landed asset that you really cannot do either from the samples or from orbit. Okay, so this is our package. You've seen that before. It was also in Seiji's talk. So this is the MASCOT. On the left-hand side is the flight model. On the right-hand side is an artist impression. It's a small package. It's like shoebox size, like this big. It's 11 kilograms. Has a high payload to system mass. So it's like 3 kilograms of payload for the 11 kilograms of lander. So if you have some mission, you're flying to a small body and you have 10 kilograms to spare, that's a good thing to take along. Now let me see whether I can do this. Okay, so I'm going to talk about 3 instruments. So we have a camera on MASCOT, takes pictures. We have a infrared radiometer, which measures surface brightness temperature. We have a magnetometer for the magnetic field measurements, and we had a hyperspectral imager, which unfortunately didn't provide any useful data because of the unexpected surface of Ryugu. We didn't get things into focus, and the laser was not in the field of view because the surface was so rough. We didn't really have anything we can show for that instrument. But I'm going to talk about the other 3. Okay, so the MASCOT mission in a nutshell. The separation was at 40 meters altitude, was all observed by the Hayabusa onboard navigation camera suite. So we have nice pictures. The first surface contact was after 6 minutes of free flight, and then we had 17 hours of surface mission lifetime. And one of my favorite pictures is this one here. So this is MASCOT just after separation, captured in flight by the navigation cameras. And we have reconstructed the trajectory of MASCOT from pictures like this one, where you can see in the bottom here the shadow of MASCOT. That doesn't work too well. Okay, anyhow, the shadow, and from tracking these in multiple images and due to the careful planning that the imaging team has done, we have many, many images where we can see the shadow of MASCOT or MASCOT itself, and we could reconstruct the trajectory from that. Okay, so this is the landing site, basically 20 degrees north, 317 east. On the right-hand side, we have a digital terrain model of the general region, 50 by 50 meters. You can read the details in Preuska's ANA publication, which has been out since a month now from now. MASCOT landed in a small depression, so this is what I call interplanetary golf tour. So you fly there, and then you just put it in the hole. It's important that we have the DTM because this is for the illumination modeling, which we need for the thermal boundary conditions when we're doing thermal inertia with the instruments. And this is one of the main ingredients here. Okay, so this is the reconstruction of the trajectory. Details of that are in Scholten's paper, also in ANA, same issue, I think. And what you see here basically is the separation point, and then we have points where we see MASCOT shadow on the surface, and we have points where we see the MASCOT itself, and you see it's a straight line as it should be. And then we bumped into this boulder here, which is about 3 meters large. So it was in the wrong place at the wrong time. We were ejected from this one slightly off, and then had another contact with the surface here, another one here, then rolled over the surface, and there you go, birdie. One of the things that we are still working on is the contact mechanics that happened around this point here. Unfortunately, as you can see, the contact happened in the shadow, so we are not 100% sure whether we hit the surface first or whether we hit the rock first. So either it was like getting down and then up again and away, or the other way around, and that of course makes a difference for the kinetics. But we still hope to be able to get some surface properties out of this surface contact. Okay. So these are images taken during descent, and Psyche has basically said all that already, so I'm not going to spend much time on this. You have different types of boulders that you see on the surface. We could identify 2. They have identified 4 in the global view, but what he said is basically seen here as well. So what you have is the majority of boulders are these very dark, rugged boulders, cauliflower-like texture, and a few, maybe 1 or 2% of the boulders, which are more S-type-like. They have different fracture patterns, they have much higher albedo, and they are also strewn across the surface. And we see the same thing as they see from the orbit. So that's a nice comparison. At the moment, I think the best midroid analogs that we have for this one is CM2 for the type 1 and C2 for the type 2 boulders, which is the dark, rugged ones. Where it gets really interesting then, of course, is if you can do close-up imaging, and the MASCOT camera has a resolution of 0.1 millimeters in the near field. So this is an image taken with one of the LEDs switched on during night. So 4 LEDs were part of the camera suite, and we have taken multiple images during the day under different illumination conditions of the same scene, and also some at night with the 4 different illuminations, red, green, and blue, and infrared. And what you see here is basically yeah, lots of texture. Of this, it's a type 2 boulder, so it's a cauliflower, very rugged texture, dark boulder. And if you zoom in here, you can see multiple inclusions, and this is a 1 centimeter length scale. And these things really look like chondrules or CAIs, and from a texture point of view alone, it is very similar to what you see if you look at meteoroids at the same scale. So this basically establishes first link that these bodies actually are parent bodies for, I mean, everybody would have expected that, of course, but this is a good indication that that's actually the case. And of course, once the samples are back, we'll know for sure. But at the time being, I think this is the best hint that we have. It's all in Ralf Jaumann's science publication that came out last year. Okay, so then we have a radiometer, and I'll talk a bit more about the thermal inertia because that question came up. So what we did is we observed the same boulder, and this is a daytime image of the same thing, and outlined here is the edge of the boulder here. The rest here is background, so that doesn't play a role. Some is from the top right, and this is the spot that we observed with the radiometer. On the right-hand side, you can see the diurnal temperature curve that you get, and this is also something you can't do from orbit, yeah? Because if you're staying in the same spot, you can do a real 24 local hours measurement and get the entire curve, which will allow you to constrain things you can't constrain from just single point measurements. So what we were able to do is we were of course able to constrain the thermal inertia, but we were also to exclude any dust cover. So what we now know is that the thermal inertia that we measure at this boulder is the bulk thermal inertia of the thing. It's not a small dust cover, yeah, because the cooling curves that you get from dust-covered boulders are just not what we see in the data. And the noise of the data is quite low, so the uncertainty during nighttime is Kelvin and a half. So this is a really solid model, and we have published this in Nature Astronomy. To be fair, we take nature and science, so not like the other mission. Okay, so this is the details of that. And of course, question is, if you have a 280 thermal inertia units boulder, what does that mean? And of course, this is a value that is very small. It's very consistent with what you see from remote sensing, but it's not consistent with what you expect for a rock, yeah? And so we scratched our head a bit, and this is what we came up with. So basically what we have here is thermal conductivity as a function of porosity, and if you convert the thermal inertia estimate to conductivity, you end up with values which are about 0.1. And you then go into the literature and want to see, okay, what does it mean? And you see that we don't have any meteoroids in the lab that have these low thermal conductivities. Everything has at least 0.5, and many of those are beyond that. So what you can still do is you can extrapolate, but of course, extrapolation is not what is easy, or yeah, if you don't have to do it, you wouldn't do it, but in this case there's no data, so you look into the models that are available, and there are multiple, and depending on which model you take for the extrapolation, you end up with porosities which are like 30-something% or even 50%. So it's highly porous stuff, otherwise the thermal conductivity wouldn't be that low, and that's the only way to be consistent with what we've seen in the thermal data. Now you can go a step further and also estimate the macro porosity. So given the boulder size frequency distribution at the surface, you can estimate how can you put this together and what's the porosity of the entire asteroid that you get. And turns out that for the things that are observed with the onboard navigation cameras, you end up with porosities that are quite low. Yeah? So you can arrange these things to porosities down to 15%, and then you can calculate grain densities. And if you play this game, I don't have time to go into details, so the publication is almost written up now. We're going to submit that beginning next year probably. You can estimate grain densities, and you get, depending on which of these extrapolations you believe, 2 different solution families. But basically for the higher porosities, you end up spot on with what you'd expect for a C-type asteroid. So that's to me pretty convincing that we are on the right track. So everything's adding up here. Okay, finally, we're going to talk a bit about the magnetometer, which was also switched on during the entire mission, so from separation to end of mission. Basically what you see here is the beginning. So when we were ejected from the spacecraft, you see the spacecraft field decaying during the first part, and down here is a zoom in on the touchdown. So you of course have to clean the data. So these things are all camera images taken, which of course the magnetometer sees, because it's not only magnetometer, it's also an ampere meter. And when you have touchdown here, something changed in MASCOT, so we can very precisely time the time of the touchdown from the magnetometer data, because something in the mechanical arrangement of the lander changed, a cable moved or something, and you have an immediate signal. And this is also information that's folded into trying to get the contact mechanics of the lander with this 3-meter boulder correct. Now, but what does it mean in terms of the magnetization of the overall body? And what you see in the top left here is basically from separation to touchdown, the detrended magnetic field measurement. So this 1 nanotesla oscillation is basically what you would expect from the solar wind. And what you don't see is an increase in signal. So this basically means that at the larger scales, this body doesn't seem to be magnetized. At least the 3-meter boulder doesn't give you a signature that you can measure at 1 nanotesla resolution. You can do then models and try to estimate what the magnetization is, and it turns out that it's 3 × 10⁻⁶ ampere square meter per kilogram. We know that carbonaceous chondroids are more magnetized than that, but we don't see a signal here. And that can only mean that the magnetization of these bodies, if it's present, is at very small scales. So they are not magnetized on the boulder level, but on like 10 centimeter level. Yeah, and that's also interesting in itself. So I think I don't have time, so I'm just going to leave the conclusions up here. So I think the main things that we have is we have good identification of inclusions, so that gives us a link to the meteoroids. We have a very high porosity that we've determined from the thermal data, and we know that these things are not magnetized. One of the things that's interesting for the parent body is that the high microporosity has some implication on what type of body this can actually be formed in. And Vladimir Neumann has a paper in preparation where he's talking about the sizes of parent bodies that are consistent with this high internal porosity, and turns out that these can't be very large, few kilometers, otherwise they, like through hot pressing, they will not have the porosity left, and then you would not get the boulders that we see here. And I have half a minute left. Thank you.
That's half a minute over.
Oh.
Thank you very much. Listen, I'm sorry, we don't have time for a question. We're going to have to move on. Lightning, this is great. Okay, the next talk is going to be the artificial impact crater formed by Hayabusa 2, the small carry-on impactor on the surface of asteroid Ryugu. And the talk is going to be given by Masahiko Arakawa.
Hi, hello. I'm Masahiko Arakawa, coming from Kobe University, Japan. I'm a science PI of SCI and DKM3. So as you know, impact process in the solar system is a fundamental physical process related to the collision evolution of planets from planet to Mars. So especially, impact cratering is one of the most important geological process on the surface of solid bodies. So the crater scaling laws are necessary to estimate the scale of planetary impacts on the surface. So a lot of efforts of laboratory experiments and the numerical simulations have been conducted to construct crater scaling laws. So the impact experiment on real asteroid is a good opportunity to confirm and improve these crater scaling laws. So this crater size scaling law is necessary to construct the crater chronology on the solid bodies. So sorry. So this is an example of a crater chronology of Ryugu studied by Sugita et al. This figure shows a cumulative crater frequency, and Ryugu surface age was estimated to be 10 million years by using the crater size scaling law for cohesionless surface. But in the case of a dry soil cohesive surface, the surface age is estimated to be more than 100 million years. So that we can improve the crater chronology of asteroids such as Ryugu based on the impact experiment on the real asteroid. So the purpose of a SCA impact experiment is as follows. So we made an artificial impact crater in order to excavate the subsurface and observe the asteroid interior. So in engineering aspect, the purpose is to develop an onboard equipment for impact experiment in space. And in scientific aspect, so impact experiment can support Hayabusa 2 scientific observation by remote sensing instruments and sampling at touchdown. So the scientific purposes are related to sample science and remote sensing science and science for planetary impact process. And next, I'd like to introduce instruments briefly. So SCA is a small carry-on impactor. It's composed of a copper disk with a size of 30 centimeters and explosive. And the copper disk projectile with a mass of 2 kilograms and a velocity of 2 kilometers per second deformed to a hollow spherical shell with a size of 30 centimeters. And this is the first instrument to form an artificial impact crater on an asteroid. And the DCAM-3 is a deployable camera in third generation. This is a tiny satellite composed of optics sensor, transmitter, and battery. And the spatial resolution is better than 1 meter per pixel, and it can take an image every 1 second. And it has a wide field of view of about 74 degrees. So it enables us to make an in situ observation of SCI impact on the surface of Ryugu. Next, I'd like to show the SCI operation briefly. So SCI was separated from the Hayabusa 2 about 500 meters above the Ryugu surface. And then the SCI descended gradually toward the Ryugu. And after the separation, the Hayabusa 2 escaped from this position very quickly within 40 minutes. And this evacuation process, the DCAM-3 was separated at this position in order to observe SCI impact. And then the Hayabusa 2 continued to escape until the safe zone behind the asteroid. After the Hayabusa 2 was evacuated completely, so the SCI was detonated, and the DCAM-3 observed this impact. And I'd like to summarize the impact experiment by SCI. So impact experiment was conducted on April 5th this year. The DCAM-3 succeeded to start prior to the operation and worked for more than 3 hours. And the impact ejector after the SCI impact was successfully recorded by DCAM-3, and success of SCI impact was confirmed by DCAM-3 images at first. Then, impact crater was identified by ONCT camera on Hayabusa 2 3 weeks later. So impact point was close to the aiming point of the equatorial bulge, like here. So next, I'd like to show the original image taken by DCAM-3. So DCAM-3 rotated very slowly in order to stabilize its position. So the Ryugu rotated like this. By using this image, we analyze the ejector curtain growth. So here is a successive images of ejector curtain growth. So the first image, A, is taken at 5 seconds after the impact. You can see the ejector curtain around here. So we find that the continuous crater growth was observed for at least 500 seconds. The impact ejector developed northward at first, and the ejector curtain was never detached from the ground. And the ejector deposition was found at later stage after 400 seconds. So we think that the SCI crater could be formed in the gravity-dominated region. So I've showed the video of ejector curtain growth. You can see the ejector curtain around here. So you notice that the Ryugu rotated a little. So this is a close-up image of a video. Please enjoy it. I come here just to show you this image. Okay. So I'd like to summarize the curtain and the ejector deposits. So this image A is taken at 200 seconds after the impact. You can identify 4 ejector layers in the north direction, but we never observe ejector curtain in the south direction. So in order to study the ejector distribution, we construct the ejector distribution map on the surface of Ryugu by using this image. So you can notice that 4 ejector layers and with continuous curtain in the north direction, north region, but we never observe ejector curtain in the south region. And this image is a map of ONC reflectance factor difference between before and after the SCI impact. The black region corresponding to the ejector deposits. So we notice that the 4 elongated area, 1, 2, 3, 4, you can see it. So this distribution is very similar to the ejector distribution map of the middle image, this one. And next I will show the observation impact crater. So this image was taken at before and after the impact. So you can recognize a very large impact crater at the center of this image. And so SCI crater has a semi-spherical shape like this. And you can find a very large block inside the crater with a size of 5 meters. So this is a close-up image of inside the impact crater. So you see the pit-like structure at the center of the impact crater. Next, I will show you the crater morphology. So this is a digital elevation map of the SCI crater. So I will show you the cross-section of this crater along the traverse line A and B, here, A and B. So SCI crater has a semicircular shape because a large block stopped the crater growth towards the south region, we think. So crater major axis is about 18 meters. So this corresponds to the crater rim diameter. And the crater diameter is about 15 meters. So it was measured at the pre-impact surface. That means the crater radius is about 7 meters. So we can calculate the crater radius by using a pi scaling law applied for Ryugu when we assume the cohesionless sand. So the calculated result is about 7 meters. So this result is very similar to our observed result. So we think that the Ryugu surface could be made of sun-like cohesionless material. So we also found a deposition limb with a height of 40 centimeters around here, and the crater floor with a depth of 1.7 meters. And this is a summary of my talk. I just emphasized that the SCI crater diameter is about 15 meters. This size is explained by the surface covered with a sun-like regolith without cohesion, and the SCI crater could be formed in the gravity-dominated region. That's it. Thank you very much.
We do have time for questions. Nancy?
Congratulations, this is amazing. I think we all are in awe. That's an amazing video.
Thank you very much.
It's interesting to hear the talk before you with the low porosity, and maybe that's feeding into what you're seeing with this gravity dominated. Have you thought about how those two combine, what they might mean for what MASCOT is seeing with the porosity and what you're seeing here?
So I think that the porosity is large, but this border has some strengths. That means our impact does not destroy these borders. So the crater was formed in the gravity-dominated region, we think.
Any other questions? That is an amazing video.
Excuse me?
Yes, who's asking?
Yep.
Sorry, couldn't see.
Here you go.
Can you say anything about the age of you of the SCI experiment?
So I think that Sunita-san explained about the age of the Ryugu. So depend on our results shows that that age is about 8.9 million year. I think that. Not the dry soil cohesion scaling is not suitable for the Ryugu.
Okay, thank you.
Thank you so much.
Thank you. Okay, and the next talk, we're going to change our focus here a little bit from the Hayabusa 2 and OSIRIS-REx missions, and we'll talk about a little bit more about planetary defense with the DART mission, the Double Asteroid Redirection Test mission, with the talk being given by Nancy Chabot.
Great, thank you. I'm really happy to be invited into this section and to be here as a representative of the much larger team to tell you about a small bodies mission that's upcoming in the future with a slightly different motivation than the ones we've been hearing about so far, and that's DART, NASA's first planetary defense mission. So what is DART? DART is the Double Asteroid Redirection Test, and it's going to be the first mission to demonstrate asteroid deflection with a kinetic impactor. Put more simply, we're going to purposely crash a spacecraft into an asteroid. So yay. There we go. Yeah, but really that's the mission. We're launching in July of 2021, impacting in September of 2022. This is a NASA mission being managed and built at the Johns Hopkins Applied Physics Lab, my home institution, but we have a number of partners who are also contributing, shown there along the bottom. So a few more details about DART and the target. So the target for DART is Didymos asteroid. It's important to state straight up front that Didymos is not on a path to collide with the Earth. This is a test. It is only a test. But that makes it inappropriate for the first test. And Didymos actually is a binary asteroid system, or a double asteroid system, hence the name of the mission, Double Asteroid Redirection Test. And so there's two asteroids in this system. There's the main asteroid, Didymos A, 780 meters in diameter, and then the smaller asteroid, Didymos B, which is actually the one that DART is going to impact into at 160 meters, and it orbits around A about once every 12 hours. And so DART is going to come speeding in at 6.6 kilometers per second. That's about 24,000 kilometers per hour. It has a camera on it, and so it's going to get high-resolution views of that impact site for sure. And about 5 days ahead of time, there's a CubeSat, Licia Cube, the light Italian CubeSat for imaging asteroids. This is contributed by the Italian Space Agency, and it's going to get deployed 5 days in advance. And it will be able to also image the impact event, and then it will make a close approach by Didymos B about 3 minutes later, and then continue speeding on its way and be able to see the other side of Didymos B as well. But what really makes this an ideal target for this first test is the fact that it's a binary asteroid, and it's an eclipsing binary asteroid. And because the critical measurement of how much deflection are you going to make comes from how we're going to change its future path, its trajectory, its orbit as it goes around. So DART's going to come in, hit it nearly head on, and it's originally on that white orbit like you see there. And then it's going to be on this new orbit, this blue orbit, exaggerated. We think we're going to change it from 12 hours roughly right now to be about 10 minutes shorter. So about a 1% change, but we don't know the exact value, which is why you have to do this test. But we can't make those measurements. The spacecraft's going to get destroyed. Licia Cube's going to go speeding by. Earth-based telescopes. So existing telescopes that are here on the Earth using these existing assets are going to make this crucial measurement by observing how much that period changes from there. And this really allows this to be a very cost-effective, highly focused way to do this first mission by using these existing telescopes on the Earth to make this critical measurement of how effective is something like a kinetic impactor at deflecting a real, actual asteroid. So DART's level 1 requirements define the planetary defense investigation that we're doing here. And the first one is to impact Didymos B, and to specifically do this during this September-October 2022. That impact date is when the distance between Earth and the Didymos asteroids is minimized. So this is when the telescopes can make that crucial information about what that orbit change is. So it's very important, and that's why this September of 2022 is the key time in order to do this mission. And then to change its binary orbital period, to measure that change in the orbital period, to measure beta, which is the momentum enhancement factor. So how much more momentum do you get because ejecta is going to spew out along with your spacecraft that's coming crashing in, and to characterize this impact site and dynamics. And DART is really well aligned with the recommendations for what the National Academy's Defending Planet Earth study recommended in 2010 for the top priority for a mitigation mission if you were going to do this to address the asteroid hazard. And this is a graph, a figure that was from that report in 2010. And on the y-axis, you see the diameter of the asteroid, and on the x-axis, you see warning time. Because it's also important that this is not something that you just do at the last minute, despite movies, right? That this is something that you give it a small nudge, and then it adds up to a big change with time. And so warning time is crucially important with any of these planetary defense things, because you're not trying to disrupt the asteroid, you're trying to deflect it. And the kinetic impactor was rated as the highest priority to do first because this is really where the potential hazard exists out there in the near-Earth asteroid population. So for objects that are about 1 kilometer in size, we found about 90% of those, and they hit maybe every few millions of years. But for things that are more like the size of the DART target, where the kinetic impactor is really the technique that you would do, there's roughly 25,000 of those out there. We've only found about 1/3 of them, actually, at the moment, and we're talking about thousands of years that is the impact frequency for something like this on the Earth. So that's why that was the top priority, to start to be ready in case we did need this technology in the future. So a few other technologies on DART, other than demonstrating this kinetic impactor technology. It has an autonomous smart nav system, and that's because Didymos B is so small and you're coming in so fast that you can't actually make it out from the bigger asteroid until the last hour of the mission. And so you can't actually see the target that you're going to hit until the last hour of the mission with the camera. And so you have to do that all on board. And so that's where the smart nav system comes on to autonomously target on to hit Didymos B. The camera that's on board is based on LORRI, which took spectacular images on the New Horizons mission of Pluto. It's going to be NASA's first flight of the next sea ion propulsion engine, so the next generation of this ion propulsion engine, and we're excited about that. And it's also got rollout solar arrays that will roll out in space, and once they're deployed, they're going to be about 19 meters tip, tip, tip. And I just want to show this little video while I talk about it. And that's because DART is moving forward. Everything is a go towards launch. We've had some milestones come up. Critical design review successfully passed in June of 2019. Mission operations review in September of 2019. Both of those are done. We're looking forward to the integration readiness review coming up in March of 2020. And then key decision point D in April of 2020, and that'll let the mission go on to full integration and testing and ultimately launch in 2021. So, and it's always nice to see some real hardware actually coming together. So I have some joke about I like the high-paced atmosphere that we have at 8PL2, but everybody's really excited. This mission is on track for a launch in 2021. So to put this in the bigger context, just sort of briefly, you really wouldn't do something like DART in isolation, right? This is all part of a much larger planetary defense strategy. It's crucially important to assess the objects that we know are out there and keep track of them, but also to search and detect and track and identify what this population is, figure out what the potential hazard really is by doing that. Characterizing these objects. So this is a lot of crossover between a planetary defense mission and a science mission, if you will. Everything that we've heard about OSIRIS-REx and Hayabusa 2 feeds very much into what we can know and what we would know about these objects. Plan, coordinating. This is not a NASA-only effort. There's international working groups and international committees and communities that are involved in all of this, and that's important. And then there's mitigate. And that's in case you need it, let's be ready. And that's where DART comes in. And I just wanted to end with this final slide talking about AIDA, the Asteroid Impact and Deflection Assessment. And that's because international cooperation is really needed for an international issue like planetary defense. And so DART is a NASA mission. It's going to impact in 2022 into this Didymos system. But then ESA just a few weeks ago gave the green light go-ahead in order to do the Hera mission, which is going to rendezvous with the Didymos system in 2026. And so by rendezvous, they're going to be able to do a very detailed, in-depth look at what the impact crater that was made by DART, what the mass of Didymos B is, and much more. And this sort of combined collaboration internationally is really going to increase the knowledge that we get from this first planetary defense test on a real-sized asteroid. Thank you.
Time for questions? Yes.
Do you have any plan to have an in-situ observation from the ground? I mean, do you coordinate with Hawaii or some other telescopic site at the time of impact, like the deep impact?
Yeah, absolutely. We're going to have an international observing campaign where everybody will be welcome to contribute. We've got a few facilities that we'll be specifically putting under contract for DART to make sure we get the data that we need to get to meet the level 1 requirements, but we fully anticipate that the participation will be international in all observatories everywhere. In fact, the 2022 opportunity is so favorable. It's sort of a magnitude 15 when this object is coming by, and so telescopes smaller and smaller are really going to be able to contribute and we're going to be setting that up. Christina Thomas at the Northern Arizona University is leading that, and I'll be leading that campaign. So everyone will be welcome to contribute.
Heather?
So Rosa deployed on the space station already. There's some cool movies online where you can go and look out on that. And I think it's getting picked up in some other mission concepts sort of there, but we're excited to use them. And it's very enabling because they're light mass when you sort of take off and everything. And DART has had an interesting history of maybe being a ride share and then now being a dedicated launch and things like that. So, yeah.
Nancy, can you tell us what's the payload on the Hera spacecraft?
I probably shouldn't because I don't really know exactly all the details. I know the camera, based on Dawn, is their one critical sort of threshold payload that they absolutely will have, and then they have a number of other things that are under consideration or looking at, but I'd welcome if somebody else here in the audience is more up to speed on that. As you can see in the animation shown here, they are also planning to carry 2 CubeSats, which would have additional information, and they're planning to also land on the asteroid. And it's gone through a lot of variations over the years, and I think we're just excited that ESA gave it the green light and that we can all collaborate going forward.
That's great. Time for one more question?
Okay. Oh,
Yes, go ahead.
Yeah, the accuracy of the impact, right? I mean, so this is a 160-meter diameter sort of body, right? I mean, and the phase angle when you're coming in is at like 60 degrees. So part of it's in the dark as well. And so we're doing plus or minus 15 meters, 1 sigma. So plus or minus 45 meters, 3 sigma. And the smart nav system has been performing within that with all the tests we've been doing. We've been throwing crazy shapes into there because we really don't know anything about Didymos B, very, very little about what it's shaped like, what it's going to look like. And so to be prepared for all those contingencies, it's been performing very well. It is targeted a little over towards the sunlit part of the surface as compared to the shadow surface, but they were actually taking saturated images to try to get it more towards the center. But with the plus or minus 15 meters accuracy, 1 sigma that we have as a requirement, we're confident that it's going to hit.
okay, let's move on. The next talk is, just a second. Okay, so building a mission to unknown body constraints on the composition and formation of 16 Psyche. The talk is led by Lindy Elkins-Tanton.
Thank you. Thanks a lot. Happy Friday afternoon, everyone. Thanks for being here. This is such an interesting and fun talk for me to give because at the time that we proposed to go to Psyche, most of the planetary science world was fairly sure that Psyche was the stripped metal core of an asteroid. And of course, as soon as selection occurs, so many more people look at it, and we're getting more data, and it's becoming more confusing by the day. And so I'm really excited to talk about where we are with that, because that's part of exploration. So to remind you all, Psyche is a fairly large asteroid. If we were unfortunate enough to drop it on Arizona, it would go from Flagstaff to Phoenix. It's about the size of Massachusetts. This was the original idea of how Psyche might have been formed. Reading from the top left to right as one would a book, a differentiated planetesimal, which is really our science interest, what happens with these planetesimals when they differentiate into core and mantle, struck by a hit-and-run collision. Probably actually 4 to 8 hit-and-run collisions would be required to strip off the silicate exterior and leave the metal core. We very much hope that it formed a core dynamo and recorded its magnetic field in its crust of metal as it froze from the outside to the inside, and eventually was knocked over so that its spin axis lies near the ecliptic where it is today. So that's our concept cartoon from the concept study that we did, but now that's almost certainly wrong. I suppose at the time it was almost certainly wrong too, because we really don't know what things are till we go visit them, and so that's part of the thrill. So this is a reminder, we do not know what Psyche looks like. We've never seen a largely metal body up close. This is Psyche from my backyard. Psyche from the Wilson 60-inch doesn't look too much different, and frankly, neither does Psyche from the Hubble Space Telescope look that much different. We do not know what it looks like, and we don't really expect it to look like the other asteroids that we visited, but who knows? So what can we tell you about it now? The three most recent shape models for Psyche, the effective volume agrees within 10% at their central values and within 30% at the extremes of their 1 sigma errors. So that's not too bad. We think that we have a decent idea of its volume, although a 10 to 30% error is still going to make a big error on density, which is where I'm going next. But before density, let's talk about other measurements that we can make from Earth that might tell us what Psyche is made of. First, thermal inertia. At the time that we wrote the concept study, the value was the 243 to 284 from Matter et al. 2013, and everyone was like, yes, it's made of metal. And then Landsman 2018 came in with 11 to 53, which is right like Vesta. So this is actually inconclusive and not resolved right now. So that's a really interesting problem. We really need to know what the thermal inertia is, although thermal inertia, of course, is a conflation of many parameters, not just the composition, but also grain size and porosity and other things that we can't constrain right now. So radar albedo, we still have high disk averages that is supportive of metal on the surface. And so now we're, what is it? Okay. Now, this table I'm not expecting you to read, but I want to show it to you because we've been collecting the mass estimates, which are the left-hand column, the density from the reference from as far back as 2000, and so these are in chronological order from the top to the bottom. You don't have to figure out the numbers right now because I'm going to show them to you in a graph in a moment and make sense of them. But the thing I was reminding myself to do with this slide was not only show you the number of data that we've gathered, but also to say that we have recalculated the masses into densities using the Viken-Koski 2018 volume, which is our team's preferred volume right at the moment. So we've recalculated the densities from these papers using that volume. And so this is the graph that we get with the year of publication on the horizontal axis and the bulk density of Psyche on the vertical axis. You can see we've got some outliers that would be non-physical, I think. You can see the red line there, which is the density of camosite. If it was a pure iron nickel core, then it would be perhaps near the density of camosite. Down lower is troilite, which is iron sulfide, FeS. And then below that, there's a blue line, which is the density of Vesta. And below that, a red line, which is the density of enstatite, which is a very iron-poor pyroxene, which is one of the candidates for the rock portion of Psyche. And you can see that there are values all around the place, although many of them are focused in the last, say, 10 years. And so let me blow up that part of the graph for us to look at more closely. Now, the yellow value that you see there is our team's functioning value, the value that we're using right now, our fiducial value. And what we did to achieve that yellow value is we took the Barron-Chesley 2017 mass with a 1 sigma uncertainty that's 2 times larger than their formal error, and we used the Viken-Koski volume, that has an effective diameter of 226 kilometers, and that gives a bulk density of Psyche of 3,780 kilograms per cubic meter with a 1 sigma error of 340. Very interesting, the Siltala measurements that are the low density ones that are that have been accepted for a publication but not yet published there, they do have overlapping error bars. They use a different calculation method, and so it's going to be very interesting to see where we end up with this. But with our fiducial density, Psyche is denser than Vesta, among the densest of all asteroids, but definitely not pure metal, definitely not. And so let's take that and put it into a ternary diagram. Let's imagine that Psyche is made of pore space, which is at the top of this triangle. So if it was actually just a vacuum, it would plot at the top. Iron metal, which is the left-hand apex, and some non-metal component, which is the right-hand apex. What we've done is we've imagined that we have that density that I showed you, our fiducial density, that is composed of a mixture of iron metal and some non-metal density that you can see in the legend between 2800 and 4800, which is more or less anorthite, that is feldspar up to troilite. And we can argue for the unnatural idea that you could have anorthite mixed with metal. So the point is not that we think it makes petrologic sense, but just to look at what the compositional thing could be. And you can see there are a couple of points there that I'm marking out, A, B, C, and D, that I'll talk through one at a time. So A is if you have absolutely no non-metal component, with our fiducial density, Psyche would be 48% metal and 52% pore space. Now a question would be, how much pore space can iron, nickel, metal support before it is going to crush the pore space out? And that is an unknown question, because we do not know the strength of iron, nickel, metal at the temperatures of Psyche. And in fact, we don't even really know the temperatures of Psyche yet. There has not been a good model of that. With its spin axis lying in the ecliptic, when that spin axis is pointing at the star, the pole gets nice and toasty, and the other pole gets really cold. And then when it's in rotisserie mode, being shined on its side, so it's going to be quite a complex thermal model as well. Now, point B here is 2 sigma away from our fiducial model, still with no non-metal component, would be 57 volume% metal. Down here with C, if there's no pore space at all, then it could only have a maximum of 13% metal under our current scenario. That's very unlikely. More likely would be something like 20% pore space compared to other bodies that we know about. If the other component is something like pyroxene, which is supported by the spectra, incidentally, any kind of iron-bearing silicate not supported by the spectra. So not the olivine that's in palisite and not the silicate that's in mesosiderite, interestingly. Those are ruled out by the spectra. Then we would have something like 25% metal. And so CB chondrites, actually, Ishiyevo in particular, is one of the best fits for spectra and density, which would be fantastically bizarre if we went out there and found it was that. And so finally, our tagline all along has been Journey to a Metal World, but now it's Journey to a Metal World. Psyche's bulk density appears to be between about 3,400 and 4,100. It's predicted, therefore, to have between, say, 25 and 60 volume% metal. The reflectance and optical properties indicate non-uniquely that the surface may be largely metallic. I'm sorry, I didn't mean to go past that. And so what I'm left with here is, I think, in a really extremely exciting situation. I was really thrilled to be going to see Psyche when we thought it was a core. Now, if this information is right, it's something even more bizarre and difficult to explain. And to me, that's really beautiful. And the one thing that I can be fairly sure of is probably almost everything I reported today will be proven to be wrong when we get there. And so stay tuned as we find out what this mystery asteroid is. Thank you very much.
Several questions. Hal?
So I'd like you to comment on how well you think you actually know the volume,
Yeah.
right? Because these are all inverted light curves, right?
Yeah, they're radar, light, and occultation. So it's hard to say. You get just not about volume, but if you talk about like the thermal inertia, those two sets of measurements, the error bars don't overlap. And so taking what I read at face value, I go back to those 3 shape models that are recent and say we probably know it to within 10 to 30%.
Okay. We have deployable telescopes that do occultation.
Yes.
The occultations of the Lucy targets. We should talk
Yes.
about the idea of whether we can use that to observe this.
That would be great. We've been talking about that, and there was a series of occultations of Psyche taken about a month ago, actually, so there's new data just coming out on that.
Okay.
Yeah, love to, absolutely. Invite the world to help us figure out what this thing is. Time for one more, I know.
One more.
Yeah,
Thank you. Nice.
thank you.
This session named the journey to the origin of the Earth. So what is Psyche's view or Psyche's contribution
Yes.
to the origin?
Thank you. I meant to say that, and I didn't. I love that we're going to these small bodies that are also extremely different. And my usual metaphor is if the Earth is the cake, we really want to know what the flour and the eggs are. And, we're going to chondritic things that are sort of like the primitive component. And then I would say, well, Psyche is another one of the components, because almost certainly everything that built the Earth to first order was itself already differentiated. Only now that we're not really certain, is Psyche a breccia from 2 embryos that impacted and mixed? Or is it a CB chondrite, something super reduced that never melted? It's going to be a bizarre ingredient to the building of habitable planets. And so I have a less clear answer to that, except to say that I think in general, our view of small bodies, how they form, how they relate to planet building is in its infancy. I think we have a very narrow view of this, and I'm hoping that this will spread out our understanding. Yep.
Let's thank
you
the
very much.
speaker. Thank you. All right, so next speaker is Hal Levison. The title is Lucy, First to the Trojans.
So I managed to get my talk, I give a lot of these talks, down to 19 slides. So we'll see if we can, it's actually true, but.
So excited.
This is very exciting. All right, so Lucy is a tour of the Trojan asteroids. It's part of the 2014 Discovery mission selections. We're going to launch in 2021, which is less than 2 years from now, like 672 days. Scares me. We have structures and things and real hardware. We're going to fly by a main belt asteroid in 2025 as a rehearsal, although it's cool too. Have 5 Trojan encounters between 2027 and 2033 for a total of 6 Trojans, because one of them, which is my favorite, is a binary. So let me start off by saying this is our scientific motivation. I'm a theorist, right? So this is what I think the impact of understanding these bodies will have in our understanding of the formation of the solar system. But I should point out here that we are going to a population of bodies that we have absolutely no idea what they are, right? We've never visited them with the spacecraft. And because of the proximity to the orbit of Jupiter, they're not supplying meteorites to the Earth. So we really are clueless as to what these things are. But given the very limited range in semi-major axes these objects inhabit, it's surprising that they are actually not a homogeneous population. That we see objects that are C's and D's and P's. You can see the albedo plot over to the right. Albedos from 3% up to 13, 14%, for example. This diversity is likely the result of planet formation, right? How things formed and how I think, in particular, this is why I'm interested in it, being one of the developers of the NEAS model, right? How things mixed up during the evolution of the solar system and got delivered into the Trojans. So they give us a unique opportunity to understand the processes of planet formation and planet migration. However, to understand that diversity, we have to understand, or to get our full impact of these objects, we have to understand that diversity, and that's what Lucy is intended to do. So now I'm going to show you all my 19 slides in a minute and a half, right? The key of Lucy is its trajectory and to be able to visit a large number of objects in a short period of time. So I'm going to just go through what our trajectory looks like. We launch in October of 2021 on a very small rocket, an Atlas 5401, the smallest you can get, with a small escape velocity from the Earth. So we're going to go into an orbit of 1 year, and then we're going to use Earth encounters to pump up the aphelion of the object until we can get out to the Trojans. Our first gravity assist is exactly a year later after launch. Our altitude is 300 kilometers, thereabout. Right? So think about it. I just want you to think, because we're going to try to do this. This spacecraft has 7.3 meter solar arrays, and it's getting 300 kilometers from the Earth, right? So hopefully we're going to be able to go out and see it after it launches. You'll get a budget for that. Okay.
No doubt.
So we're going to use Earth encounters to pump up the aphelion, like I said. So we're going to go into a 2-year orbit. Have another EGA, which is going to kick us out into the Trojans. On the way out, we're going by a named out asteroids, about 5 kilometers, that we named after Donald Johanson, the discoverer of the Lucy fossil. By the way, this is a member of the Aragoni family, for those of you who know what that is. It's a very young family, so that's going to be cool in and of itself. Then we're going to go into the L4 and have 4 encounters. The first is Euripides. Euripides is the largest member of the only disruptive collisionally family in the swarm, and it's a C, which makes it rare. So that'll be interesting. 34 days later, we go by our second object, Ptolemy, about 20-kilometer size objects. Lucas. And by the way, between Ptolemy and Lucas, we are going to be further from the sun than any other solar-powered spacecraft in history, which is why we have 7.3 meter arrays. And then OSIRIS. And you can see, remember I said there's C, D, and P type asteroids in the swarms. So just coming out of the L4, we are covered that diversity. We're going to use EGA again now to target the one object that we have in the L5. We could have chosen more objects in the L5, but we wanted to go to this one, which is the binary, which is probably a leftover from the formation of the solar system. This is very similar to what kind of things you see in the Kuiper belt, but don't see in the inner part of the solar system. And by the inner part of the solar system, I mean inside the orbit of Neptune, right? So these are 2 100-kilometer size objects on a circular orbit around each other with a semi-major axis of about 700 kilometers. So there are our babies. So these are flybys. The encounter, I said, remember, diversity is the key, and I showed you this plot of albedos. The blue dots represent the diversity of the known Trojans measured by Ys, and the red shows our targets, so we really are covering the diversity quite well. And these are flybys, right? We're having encounters between 5.8 and about 9 kilometers a second. These are going to be really fast, right? If we blink, we'll miss, okay? But we're doing just about everything you can imagine doing in a flyby. We're going to look at surface geology, we're going to look at color, we're going to look at composition, we're going to measure masses by looking at Doppler shift as we fly by, and of course look for satellites and rings. There's the spacecraft. To put things in context, our high gain antenna that you can see over there is 2 meters. The solar arrays are 7.3 meters. Tip to tip, the spacecraft is 50 feet. So we'd probably fit in this room, but just barely, right? It's 15 feet tall. The structure is now complete. I saw it on Monday. It was cool, but it's big. So I'll end there and take questions. Thank you. Oh, it's still green. And it was 19 strong.
So, the questions?
Hi.
Yes, sir.
Yeah. Looks like it's going to be in a really interesting orbit, so it's probably too early to ask this question, but what are possibilities for extended missions?
We can go to Psyche. It's actually true.
Seriously?
I'm serious. We do have a list of targets after the extended mission, right? That's available, right? I'm a little worried, right, because of the way we fire our main engines is with a ladder of pyro valves, and we'll use them all. So you'll have to be careful about what you would do with it after. But that orbit that it's on is stable for 1 million years. So there'll be plenty of time to use the spacecraft to do other things and go back. There are Trojans on the list. There are Hildas, which would be really cool on the list. Lots of things we can do in an extended mission. But I'll be retired.
Awesome.
Yeah.
So these objects are in the solar wind when they are orbiting when they are in the Kuiper belt. Is that correct?
Say again, I'm sorry?
They are interacting with the solar wind in their orbit.
Oh, yeah, everything is.
So do you think that interaction has any effects in the morphology of the surface?
I think that it might have a lot of effect on the colors, okay? And in particular, I don't know if it's particles or radiation, but we are clueless of what makes the red things in the outer solar system red, right? We really have no idea, and space weathering is probably the prime candidate. I don't know if it's solar wind or radiation from the sun, but it's something like that.
So do you have any ways to gauge the effects of the solar wind on these objects?
Our experiment is designed to look for the reasons for the reddening. And the way that we're doing that is by, our cameras are designed to be able to see young craters on the surface of our bodies. And in particular, the red ones, the expectation is if the reddening is due to some kind of space weathering, the young craters should look gray, like Euripides. We'll see, but that's one thing we're looking for.
Thanks.
Any questions? Okay, I have one.
Oh,
Is that okay? Oh,
Yeah.
Well, go ahead. Okay. Okay, so I was really curious about the binary system, which has almost the same mass ratio. I was thinking how, well, so you mentioned this binary system may be sort of primordial.
yes.
I was thinking the connection between the evolution of the trajectory of this system to go to Trojan asteroid region because of the really high dynamical perturbation. Given this, maybe the trajectory, the system of the binary would be perturbed and then eventually maybe like escaped or maybe like contact each other.
That's actually, there's a paper written on that, which I think I'm an author of, not sure, by David Nasvorny at Southwest. He's looked at, so the story that we would tell is that all these objects formed in a belt of material between about 15 and 30 AU that got disrupted by the migration of the planets. Yeah. That's the story we would tell. He's looked at the survivability of binaries like Patroclus into the Trojan swarm and finds that there's about, if I remember the number, it's about a 1 in 1,000 chance of these things surviving. If you look at in the cold classical Kuiper belt, over 50% of the objects there, which have not been affected by the growth of the planets, appear to be these binaries.
Okay.
So if all that story holds up, this could easily be a leftover from that early period.
Okay.
But it means that early on, all objects around 100 kilometers were in binaries, which I think is a really interesting result.
Yep. Interesting. Okay.
Okay, thank you.
Thank you so much. Let's move on to the next talk.
Oh, the beer's gone.
All right. Next talk is given by Grant Jones. The Comet Interceptor, an ESA mission to an ancient world.
Okay, thanks very much. Good afternoon, everyone. Almost evening. So thanks for coming along, and thanks also to the conveners for including this presentation and this great session on ongoing and future small body missions. So I'm describing and presenting a mission that was selected by the European Space Agency about 6 months ago, which we're extremely excited about, and I co-led the proposal with Colin Snodgrass at the University of Edinburgh. So I'm sure everyone in this room is familiar with the beauty of comets and how much we've learnt from them from the ground, and of course many of the big discoveries were made once we were able to travel to them. In 1986, because we knew that Comet Halley was on its way, many space agencies prepared missions to this target, including ESA's Giotto spacecraft, the first planetary mission from ESA, but it was part of an armada, so the Soviet-led Vega 1 and 2. Also from Japan, there was Suisei and Sakikake as well, and a wealth of data was returned from all these missions. And of course, more recently, we've had Rosetta. So rather than a fly past of a comet, as carried out by NASA's Deep Impact Stardust and other missions, Rosetta traveled out almost to the orbit of Jupiter and came inbound with a short period comet, saw how it developed as it approached the sun, and learned an incredible amount about this one object. Of course, it landed the Philae lander, which was found, its location was found on the surface just before the mission ended in 2016. So by now, through all these missions by different agencies, and a year ago, the New Horizons flyby of a Kuiper Belt object, we now have a good inventory of both short-period comets, Halley-type objects, and now Kuiper Belt objects as well. But there's one population of comets that we haven't been able to travel to yet, and that's long-period comets. So our mission is to target a long-period comet, preferably dynamically new. So in the spirit of this session, we want to go to one of the objects which was flung out of the solar system early on in its formation, or, if we're extremely lucky, an interstellar object. So why do we want to do this? So clearly, the objects that have been visited already are extremely primitive, but these are objects that have passed the sun many times. They've been modified by heating, and we believe that the dust is lifted off the surface by sublimation. A lot of it falls back down. That's why the albedo of many of these bodies is so low, because they're covered in dust mantles. A dynamically new comet is one that's probably nearing the sun for the first time. We may see more of the pristine ices on the surface with less of a dust mantle. Obviously, we don't know that for sure. But a mission such as this would encounter a pristine comet with surface ices hopefully visible as first laid down at the solar system's formation. So how do we want to do this? Obviously, we need to know where targets are going to be in the future to get to them. And we need enough warning to direct a spacecraft to our target. So the likelihood of this happening is increasing almost annually with the advent of new survey telescopes on the ground. And with LSST being built now in Chile, we're anticipating a big increase in the distance at which long-period comets are found. So this plot in the lower left here shows how the discovery distance of comets has increased since the beginning of the 19th century. And with LSST, we anticipate that we'll be able to find them much further out as well. There'll also be a slight increase in the number of objects found, but for us, the big jump will be in the typical distance. But despite this increase in the advance notice of when we'll know when and where comets are going to be, this is still not enough time to plan and build a spacecraft if you find it on the ground to send a mission to it. So the solution to this is to prepare a spacecraft ready to go to a comet and wait in space. So we design and build a spacecraft that's going to sit up there and can cope with a variety of comet encounter geometries. So long-period comets, their arrival directions are isotropic. They could be coming in from any direction, prograde or retrograde. And ideally, we want our spacecraft to cope with all these encounter geometries, solar phase angles, etc. So we'd like to launch to a stable parking location in space, and then in response to new discoveries of promising targets, we'd be able to get to one of these targets in typically 6 to 12 months after leaving a stable location near the Earth. So last year in July, ESA issued an F-class mission call. So this is a small class of mission. It's nothing like the scale of Rosetta, for example. So the maximum cost to ESA at the completion of the mission, at the end of the 5 years after launch, can't be more than 150 million euros. That does not include the launch. So we'd be launching with the Ariel Exoplanet Observatory. And then, as is usual in Europe, the member states of ESA fund the development of the science teams. So we'd launch with Ariel in 2028, and we'll go to Sun-Earth L2. There'll be limits on mass as well. So originally it was a ton, now it's lower. And originally it was to be essentially built around a launch adapter for Ariel, but that has changed in the last few weeks, so it will be a full dual launch. So obviously there are lots of challenges. As I mentioned already, we have to cope with lots of encounter geometries, also encounter speed. So if a comet is retrograde, like Halley was, the flyby speed might be 70 kilometers per second in the worst case. And the solution to this is we design a spacecraft that isn't necessarily communicating with the Earth during the encounter. So we've used the Halley activity level and flyby speed as the most extreme case of encounter that we'd be able to cope with. So about 3,000 kilograms per second dust production and a flyby speed of about 70 kilometers per second. So to keep the cost within the limits, we'd waited L2 for up to three years. So L2 is relatively stable, but we do need to do station keeping, and operations costs will build up during that time. And if we haven't found a suitable target within the 3 years, I mean, ideally we'd have a target even before we launch, then we do have backup comets as well, including Schwarzmann-Wachmann 3. So some of the instruments that we're carrying also, if we do go to the backup target, are ones that haven't been flown to comet missions before, so we would be performing new science even if we do go to a short period comets. So this is how the mission will work. We'll launch to L2 with Ariel, wait for up to 2 to 3 years for a new target discovery. So our spacecraft isn't carrying out the search. We're relying on ground-based observations, provide survey telescopes to find incoming objects and maybe amateurs as well. So for each possible target, we work out the trajectory, work out where it's crossing the ecliptic plane, and then if it's a target we can reach, we leave L2. As the comet's approaching the sun, its activity rises, and then we intercept the comet where it's crossing the ecliptic plane. So an example of this, a comet from discovered in 2001, has been a good example of how this was discovered, how LSST would find it further out, and how we would have been able to encounter a typical long-period comet. So this is not just one spacecraft, this is actually 3. So we'd actually have a main spacecraft with the primary science cameras and infrared spectrometer on board. That flyby would be at 1,000 kilometers. But we're delighted that JAXA will be providing one small spacecraft as well, which would venture closer to the nucleus, carrying a valuable suite of instruments to make independent observations to complement those from the ESA spacecraft. And there'd be an ESA small spacecraft as well, also targeted closer to the nucleus. So we'll get multi-point measurements of the plasma environment and complementing views of the nucleus. So this cartoon just shows what it would be like. The 2 small spacecraft wouldn't be communicating directly to the Earth. They'd be sending their data in real time to spacecraft A, the furthest from the comets. So if we do lose either of the 2 small spacecraft to dust impacts, the data would be stored safely on the primary spacecraft, which would then send the data down to Earth. So as we go past, these three spacecraft will be on almost parallel trajectories. The main science camera would be on spacecraft A, and we hope to get up to 10 meters per pixel resolution, or better, hopefully, at 1,000 kilometers. So that camera is based on the ExoMars Trace Gas Orbiter CASIS camera. And then we'd get complementary views from the 2 small spacecraft to better understand the 3D shape of the nucleus. There are also other interesting instruments on board. So we have a all-sky mapper. So this instrument on the spin-stabilized small spacecraft from ESA would map the entire sky. So we'd see the dust surrounding the spacecraft, so we can carry out polarization measurements of the dust all around the spacecraft, covering the full phase angle, and see the ion tail develop as we go past. And secondary to the science, if we have a VR helmet, then you can see the view of what it's like to float near a comet as well. So obviously we're looking at a wealth of different science topics. So the dust jets, we'd be imaging them as we approach them with the wide field all-sky camera and passing through them and detecting the dust in situ. The plasma as well, the same, imaging the ion tail and seeing the plasma changes. So right now, ESA has carried out 2 studies of the mission. So the second one has just finished this week. And then in the new year, this will be used as a basis for the invitation for ESA to build the spacecraft. And of course, we look forward to working with colleagues from Japan on the small spacecraft as well. So we had our first full team meeting last week in Granada. So obviously we're all extremely excited about this, but our target is completely unknown. Somewhere beyond the orbit of Pluto right now, there is a comet coming in, and we hope to encounter it sometime after 2028. And I'll leave that up for anyone to look up more information. Okay, thank you.
Sorry, we ran out of
I
time.
understand.
So
Yeah, thank you.
thank you so much. Okay, so today's last talk in this session, the speaker is Hikaru Yabuta. The title is Prospects for Future Analysis of the Returned Asteroid Samples in the Light of the Observation Results Obtained by HABSA-2 and OSIRIS-REx missions.
Thank you for being here. My name is Hikaru Yabuta, Hiroshima University. I'm one of the HABSA-2 initial sample analysis team members. Today, I would like to talk about a future direction of return sample analysis of HABSA-2. And in the talk title, I included OSIRIS-REx because we have important cooperation through sample science. Under the MOU between JAXA and NASA, both agencies will exchange the return sample for scientists in both nations to analysis. So this is an exciting agreement for continuous production of new scientific results from Ryugu and Bennu by novel analytical techniques across future generations. So our targets, carbonaceous asteroids, have been paid attention to, especially as possible origin of Earth's volatiles. To date, it has been understood that relative abundances of hydrogen, carbon, and noble gases in Earth are roughly chondritic. And isotopically, bulk hydrogen and nitrogen isotopic composition of CI carbonaceous chondrite-like materials were a principal source of Earth's bulk volatiles. On the other hand, CI chondrites plots on the extension of a line connecting between solar and bulk Earth, additional contribution of isotopically solar composition are needed. And CO chondrites superficially similar to Earth, but other isotopic composition rule out this group as a major source of Earth's volatiles. After all, no single chondrite group is identical in composition to that of the bulk Earth. Therefore, it is very important to explore a major type of primitive asteroids that are not necessarily represented in the known meteorite collections. So as Seiji and Masahiko presented, remote sensing observation revealed that Ryugu has low albedo and low hydration features, which is analogous to thermally metamorphosed CM or CI chondrite or very primitive carbonaceous chondrite. And in order to constrain analog material of Ryugu, we investigated a relationship between total carbon contents and reflectance at 550 nanometer. And there was a roughly linear correlation showing that the meteorite with higher carbon contents have lower reflectance. And especially mildly dehydrated CI chondrite was most similar to Ryugu, although it is not identical. And as Matthias presented, MASCOT has provided further information on potentially primitive features of Ryugu, and MASCAM revealed many bright inclusions in dark borders. These features appears to be similar to Tagish-Lake meteorite, and furthermore, MARA revealed low thermal conductivity and high porosity, unlike any of chondritic meteorites, and these thermal properties are similar to comets. So receiving the significant clues from observation teams, the sample analysis for science will be performed around middle of 2021 after the sample return in the end of next year, followed by 6 months curatorial work at JAXA. And initial analysis team is composed of 6 sub-teams that are elemental isotopic chemistry, mineralogy, petrology, coarse grain, fine grain, volatiles, insoluble organic macromolecule, and soluble organic molecule sub-team. And here I'd like to show you the recent achievements from meteoritics, which related to the observed feature of Ryugu. Matsumoto and Tsuchiyama have first time discovered fossil asteroidal ice that is ultraporous lithologies, UPL, inside of the least ordered carbonaceous meteorite Ashfar 094 by using synchrotron-based micro X-ray computed tomography. And UPLs are several micron-sized, and they are widely distributed in the meteorite matrix. And they are porous aggregates of amorphous and crystalline silicates, iron nickel sulfides, and organic carbon. And these compositions are quite similar to interplanetary dust particles and micrometeorites. And it was estimated that bulk density of UPL were 1.6 to 1.9 grams per cubic centimeter, and their porosity of 20 to 30%. The values are somewhat close to Ryugu's value. And based on the observed phyllosilicate and relatively heavy oxygen isotopic compositions, the authors suggested that primordial water ice filled the porous space of ice and silicate dust formed in outer solar system, and it was removed during radial migration from outer solar system. Then porous, ultraporous lithology must have been formed around water snow line. And in relation to migration of material from outer solar system, Fujiya measured carbon isotopic composition of calcium carbonates in Tagish-Lake meteorite, which is thought to be derived from D-type asteroid by using secondary ion mass spectrometry, secondary ion mass spectrometry. And at first, they showed that lack of correlation between oxygen and carbon isotopic compositions for various carbonaceous chondrites despite oxygen isotopic data on single trend line, which meant that there are multiple carbon sources for formation of carbonate. And of these values, calcium carbonates in Tagish-Lake meteorites contain constantly high delta carbon 13 values of approximately 30 per mil. And these high values excluded organic material as their main carbon source because the highest values of organic molecule is approximately 60 per mil, smaller than the carbonate values. So they concluded source of the high delta carbon 30 values must have been a C30 rich CO2 ice. And Also estimated ratio of CO2 to H2O of Tagish Lake ice was similar to those of cometary ice. And in organic chemistry study, we have also attempted to search for evidence of a material transport. And recently, ultracarbonaceous micrometeorites were found by Dupra et al. And Yabuta et al. And this unusual type of astromaterials contain up to more than 90% of organic carbon, and size of organic matter is very large compared to typical size of organic carbon in CM chondrites. And it contains a various of nitrogen functional group. And they contained amorphous silicate gems, but no hydrous minerals. So we concluded they are cometary origin. However, because of altered gems, our groups has concluded these ultracarbonaceous micrometeorites were formed by a very weak extent of aqueous alteration in cometary body. And later, Larry Nitras et al. Found a carbon-rich clast in Cr2 carbonaceous chondrite, which shared common chemical features with ultracarbonaceous micrometeorites, and they concluded that the carbon crust is cometary microxenolis captured by carbonaceous chondrite during a radial inward transport of material from outer solar system. So as well as leading to our understanding of solar system formation and volatile delivery to the Earth, such analytical approach would lead to set the mood for future cometary nucleus sample return. Thank you very much.
Any questions? Okay, I have a question. So right now we have two ongoing missions regarding the HABSA-2 and OSIRIS-REx, and then the samples are coming back. So how do you collaborate or share the idea between the different teams regarding sampling analysis?
Before our presentation, I asked several teams and OSIRIS-REx, and we haven't formulated details of cooperations.
Okay. But in the future, pretty soon, you're going to...
Yes, of course.
Okay. Any other questions? Just one quick question. Yes?
I'm wondering personally which measurement you are most interested in seeing when the sample comes back, which is your favorite or you think will be the most interesting?
Thank you very much for your question. I'm PI of organic macromolecular analysis subteam, so I'm most interested in the measurement by synchrotron-based scanning translay X-ray microscope to measure organic material chemical composition by using a very high spatial resolution.
Okay. Thank you so much.
Yes. Thank you. So I do want to thank everybody for hanging out on the end of the day here. I got it. And I think this has been a really, really good session. One thing I'd like to do before you go is remind you that your prize for coming to a session that went until 6 o'clock on Friday afternoon, Toshi's going to tell you about what your prize is. I'll pull it up.
The 600.
1600.
1600.
That one.
Yeah, that one.
There we go. There you go. There you go.
Okay. All right. Thank you so much, everybody, staying here. We had a really exciting session. So we would like to introduce that we have a happy hour after this. So the location is Marriott Marquee. Is that right pronunciation? Yay!
very good.
Okay, thank you. And then atrium on the second floor, just right across the registration desk, and in the lobby, at the bar in the lobby. So you should be able to find it once you enter the entrance. So we really thank you, all of you, and the speakers. We are so excited to have this session. So thank you.
Yeah, thank you.